Hello, this is the practice for 6.8. Okay, starting with number 1. The integral of the sum is the sum of the integrals, so we start with the first term. This is going to be the exponential, so it's going to be what it is, divided by the natural logarithm of the base. Minus, and the second one is going to be 1 over x, so that's the natural logarithm of the absolute value of x. And plus c every time we're doing indefinite integral, an integral without limits. Number 2, I see there's a quotient here, and we don't have any rules for doing quotient of integrals. So this is the easiest thing here is to first manipulate algebraically, so do the division. So x to the 5th over x is going to be x to the 4th, and then 6 over x. And now that we have it written like that, it's much easier to apply the power rule for the first one, the first term, and then the natural logarithm for the second term, plus c. Number 3, exponential, in this case with base e, so the antiderivative is itself. And then for the second part, for the second term, you have to be careful because this is not an exponential, there's no x in the top, so this is just a number. E is 2.7 whatever, so e squared is just a number. So in this case, it's going to be the number times x, in the same way that the antiderivative of 2 is 2x, so the antiderivative of e squared is e squared x plus c, and that's it. Number 4, it's another example of the exponential, where it's going to be itself, but divided by the natural logarithm of the base. By the way, here, for e to the x, it's also e to the x divided by natural logarithm of itself, except that natural logarithm of e is 1. That's why the denominator disappears, but it's, if you want, it's the same formula as here. And in this case, we just need a plus c, and that's it. This one, I see there's a product here, and what we're going to do is use properties of exponents first to change that. So this is x to the first times x to the 1/3. So I'm going to add exponents, and when I add the exponents, I get x to the 4/3. But also, what I'm going to do is I'm going to use a negative exponent so I can use the power rule. That's now ready for the power rule. Power rule is going to be adding 1 to the exponent. So negative 4/3 plus 3/3 is going to be negative 1/3, divided by that new exponent, plus c. We need a c as soon as we get rid of the integral symbol. And I'm going to clean that up by the divided by 1/3 is the same as multiplying by 3. And I don't know, we can keep the x, the negative in the exponent, or we can do whatever. Or you could divide it by x to the 1/3. Something like that. Number 6. Here, there's a composition of functions. There's this, but then a squared. If this were 6.9, we could use u substitution for this, since this is 6.8, and we hadn't seen u substitution yet. I'm going to do it in a different way. So the way to do that is to manipulate it algebraically first. We're going to square this. We're going to multiply 3 minus x squared. So the square of a binomial is going to be the square of the first one minus twice the first one times the second one plus the square of the second one. And now it's easier to apply the power rule here. So this is going to be 9x squared over 2 minus, this is going to be 9x minus 6x squared over 2 plus x cubed over 3 plus c. And if we want to just simplify that middle fraction, that would be 9x minus 3x squared plus x cubed over 3 plus c. Number 7, again, I see a product. We don't know, we don't have a rule for product, the antiderivative of products. There's not a product rule, or we haven't learned it yet, so we're going to multiply that and use properties of exponents. This is t to the 1/2 times t to the 1 minus t to the negative 1. So when I distribute that, this is going to become 1/2 plus 1 is going to be t to the 3/2, and then minus 1/2 minus 1 is going to be negative 1/2, so t to the negative 1/2. And now I can use the power rule here, so this is going to be t to the 5/2 over 5/2 minus t to the 1/2 over 1/2. So I add 1 to the exponent and then divide by that same exponent. And now if we want to clean that up a little bit, that's going to become 2/5 t to the 5 over 2 minus 2 square of t plus c. Sometimes it's debatable if you want to put it. It's fine if you leave that as an exponent, or if you write that as a radical too. Either of the two. Oops. Works. Can I erase that little thing? Okay. Number 8. Again, I see a quotient, so the first thing I'm going to do is divide. When I divide, I'm going to get 5x plus 1 minus 2 over x. And now I can do power rule. Antiderivative of 1 is x, and then natural logarithm of the absolute value. Number 9. The antiderivative of the first one, this is going to be power rule. And then the antiderivative of the cosecant square is the negative cotangent. So that's going to be negative cotangent. That's it. Number 10 is similar to number 6 in that we have a square there that's a composition of functions. If you could do your substitution when you've learned it. Right now I'm going to stay with expanding the binomial. So I'm going to do the square of the first one plus twice the first one times the second one plus the square of the second one. And then it's easier to do that antiderivative because I can use the power rule. Plus more of the power rule, this is going to be 4x cubed over 3 plus 4x plus c. So the 3, that's the constant multiple that can come to the front. And then the antiderivative of cosecant times cotangent is going to be a negative cosecant. So negative cosecant of x. And then the minus 1 is going to become a minus x plus c. I see a quotient again, so again I'm going to divide, and remember this is x to the 1/2, so this is, after dividing, this is going to become 1/2 minus 1 is x to the negative 1/2. X over x is going to be 1, and then 5 over x. That's before taking the antiderivative. And when I take the antiderivative using the power rule, it's going to be plus 1 on the exponent over the new exponent minus x, and then minus 5 times the natural logarithm of the absolute value. Clean up that first fraction a little bit. This is going to be 2 square root of x minus x minus 5 times the natural logarithm of x, of the absolute value of x. 13. The antiderivative of 5 is going to be 5x. The antiderivative of secant squared is going to be the tangent, and then a plus c. And that's all there is to this one. For 14, the 3 is a constant multiple, I can stay there. The antiderivative of the sine is going to be negative cosine, so that's going to be negative cosine of x. And then, as always, this is x to the 1/2. So when I add 1 to the exponent, I get x to the 3/2 over 3/2 plus c. And if I clean up a little bit that fraction, it's going to be minus 2/3, and I'm going to leave it as an exponent, and that works for me. Okay, here they ask you to find a function that satisfies the given condition, so we actually have to use the antiderivative and then use that condition to find the particular solution. Here we're finding the general solution when that's why we have the plus c. Here we're going to have to find the value of that. This is really what we're going to be doing in Unit 7, differential equations, but we already know how to do this part. So I take in a way you can think of, I'm taking the antiderivative of that side and the antiderivative of that side, except the antiderivative of the derivative is going to be the function itself, so it's almost taking the antiderivative is losing 1 prime, it's like going backwards. And then on the right hand side, the antiderivative of that, this is going to be the power rule, so add 1 to the exponent and divide by the new exponent, and then 5x and a plus c. And I can simplify that fraction. Okay, so once we've done that, the next thing we're going to do is we're going to use this condition, the fact that when t is 1, h is -4, to find out the value of c. So when this is our h, so when that is -4, and t equals 1, so I'm just plugging 1 here, this equation should work and should give us the value of c. So in this case, -4 equals 2 plus 5 is 7 plus c. So if I subtract 7 on both sides, I get c equals -11. And now that we have that c, we're not done yet because we have to still rewrite the function. So I'm going to write what I already had before. Interesting. This is not an x, this is a t all along. And then when it says plus c instead of plus c, what I'm going to do is I'm going to write that -11. Okay. 16 is very similar. They just give it to us in a different notation, but I'm going to do the same thing. I'm going to take the antiderivative of both sides. When I take on the left hand side, I get y, and on the right hand side, I get x squared minus cosine of x plus c. Again, I'm going to use this condition by saying that y is 4 when x is 0. I can find the value of c. In this case, cosine of 0 is 1, so I think c equals 5. And now I can rewrite the function with the new constant value. and that would be my solution. 17 and 18 are a little bit different because there's 2 primes, but they also give us 2 conditions. So we're going to have to do the process once. We're going to take the antiderivative and use that to find the first constant, and then we're going to take the antiderivative again and use that condition to find the second constant, the value of the second constant. So let's start. When I take one antiderivative, I lose 1 prime, and this is going to be equal to, I add 1 to the exponent with the power rule, so x to the negative 1/2 over the new exponent plus c, or I can write that down as negative 2 over x to the negative 1/2 plus c. When I apply that condition, I said that f has to be 2, sorry, f prime has to be 2 when x is 4. So negative 2, 4 to the negative 1/2 plus c. Okay, 4 to the 1/2 is a square root of 4, so that's 2. With the negative exponent is going to be 1/2 times 2 is going to be 1, so this is negative 1. I believe this is 1, and if I add 1 on both sides, I get that c equals 3. So now that I have that, I can rewrite my derivative. F prime of x is what I had before, but now instead of plus c, I can write plus 3. Okay, that's the first step. The next step is going to be, I'm going to take the antiderivative again. So now we go to f without any primes, and then I have a negative 2. When I add 1, I get x to the 1/2 over 1/2 plus 3x and plus a new constant. That we can use the same letter, that's perfectly fine here. You can use a different letter also if you wanted to. And now we're going to, actually let me clean it up before we apply that. So this is going to be negative 4 square root of x plus 3x plus c. So I also know that when x is 0, f is going to be 0. So this has to be 0 when 0 plus 0 plus c. So c in this case is 0. And now I can rewrite my solution, in this case with the new c or without any c because it's 0. Just to be clear, this is a function that satisfies this differential equation. That means that if we were to take the second derivative of that function, we should be getting that, and at the same time, it goes to this point, the function goes to this point, and the derivative goes to that point. That's what we're doing here. Okay, so same thing here. First, take one derivative or one antiderivative. The sign is negative cosine. Apply this condition. So the derivative is going to be 1 when x is 0. Cosine of 0 is 1 minus 1, so c equals 2. And now I can rewrite the derivative as negative cosine of x plus 2. And then I'm going to repeat the process. I'm going to anti-differentiate again, taking the antiderivative. The antiderivative of negative cosine is going to be negative sine, or the antiderivative of cosine is sine, but with the negative in front. Plus 2x plus c. And to find the value of that c, I'm going to use that other condition. So f is going to be 6 when x is 0. In this case, sine of 0 is 0, so c equals 6. And to finish, to write the final answer, is going to be the function that I had already, but instead of c, I write 6. And now we have a couple of questions, multiple choice in Chessboard, that include definite integrals. So before I can worry about this, I need to worry about that. So how do I do the integer of that? Well, this is one of those cases where I'm going to divide first to make it easier. So that's going to be 1 over x plus 6 over x squared. And actually I'm going to write that as x to the negative 2 because I'm getting ready to use the power rule. So this is going to be equal to the natural logarithm of the absolute value of x plus 6 over x to the negative 1 over negative 1. And here I don't need a plus c because what we're going to do is we are going to evaluate this between 1 and 3. So when I plug in 1, I get natural logarithm of 1 plus 6 times negative 1 minus, and when I plug in 1, I get, oops, forgive me, I think I have to plug in 3 first, my bad. So natural logarithm of 3 plus 6 times 1 over negative 3 minus, and now I can plug in 1, natural logarithm of 1 plus 6, and then negative 1. So natural logarithm of 1 is 0, so this is negative 6 minus 6 is positive 6, and here I get negative 2 and positive 6 is 4, so this is going to be natural logarithm of 3 plus 4, answer B. Lastly for this one, this looks very much like the arc tangent, so what I'm going to do is I'm going to pull the 4 out and say that this equals 4 times the arc tangent of x. And I have to evaluate this between negative 1 and 1. Some of you might want to put this here. I like leaving the 4 out there and then distribute if I need to. I feel like it simplifies things, but maybe not. So here I'm going to do arctangent of 1 minus arctangent of negative 1. And in order to evaluate those arctangents, I hope, however you're going to do that, I think the way that Mr. V teaches it is saying when is the slope 1? So the slope is 1 when the angle is pi over 4. And then when is the slope negative 1? The slope is negative 1 when the angle is negative pi over 4. So pi over 4 minus negative pi over 4 is going to be pi over 2 times 4 is going to be 2 pi. Answer D. And that is it for 6.8. Thanks for watching.